Hi, I'm Ben-Yaakov. This presentation is entitled Dissecting an Internet Tutorial and an Intuitive Explanation of the Schmitt Trigger. There is a relevant reference which I'm referring to, and here is the link to it. I'm going also to print the link at the page of this YouTube video that you are now watching. So this presentation is related to a tutorial that was published in this website. And in this presentation, I'm going to review the tutorial. I'm going to explain the operation of a Schmitt trigger and discuss the operation amplifier versus a comparator when used for a Schmitt trigger, and then how to set the thresholds and what is a speed-up capacitor. So what is a Schmitt trigger? Well, here I'm showing a signal, and there are here actually three levels. Threshold. There is one in red, which is a single threshold. And if the signal is passing through this threshold, and if it is a comparator, then what we are going to see are these pulses. Whenever the signal is passing the threshold, we're going to have a high level, and then when it goes below it, it's a low level, and here it's a high, etc. In a Schmitt trigger, we do have two levels. We have a high level and a low threshold level. For a change at the output, we have to pass through a threshold, but it's not enough to go below it. We have to go below another threshold, in this case here. So for this signal shown here, I'm going to have one change here when I'm passing this threshold. All these will not matter until I'm passing the lower threshold here. So this will be the change. So this is the idea of a Schmitt trigger and how it in general operates. Now we can look at it in a different way. If this is a V-in axis and this is V-out, if we move from a low level of V-in to a higher level, as we hit the high threshold, we are jumping to a change in the output. And then, however, in order to go back, we have to go all the way to the low threshold, and then we are going to have the change back to the low level of this output. Notice that if you are at a given V-in, it really depends on where you were before that. That is, for a V-in, you can be either here or here. So you might say, which is correct, that you need sort of a memory in the Schmitt trigger to know whether you moved to the V-in here or you move to V-in from here. So there is an element of memory that needs to be incorporated, and I'm going to show that. Now, the Schmitt trigger circuit was invented by Otto Schmitt, Dr. Otto Schmitt, in 1937. So that's an old circuit which has been sustaining all the time, and it's being used many times by in many designs, and it is very useful today. This is the original design. It's based on vacuum tube that were available at that time. Modern implementation would use either discrete transistors, like here is a BJT version of it, or now more common, we're going to use a operation amplifier or a comparator, and I'm going to talk about what's the difference between the two. So in this case, typically we're going to see the element, the amplification element, and then we see an input which is the reference, and then there is a positive feedback, which is very important, and this positive feedback is responsible for switching the state from one to another. And here I'm showing it a very basic concept of how it will work in the case of a operation amplifier or a comparator. So we have a signal coming in here, and here is a reference. Now, for the amplifier or comparator, what is important is the difference between the input terminal to the device, not here. So as the signal is changing and the output will respond, we are going to feed back a signal that will actually change the voltage across this resistor, thereby creating two thresholds. Because if the output is high, we have a positive voltage here, so we have to move the signal to this signal here. If the output is low, we have a lower signal here and lower voltage here, so in order to make a change, we have to go to a lower level. So by this positive feedback, we are actually providing these two thresholds. So let's see how it works. Suppose I have a signal that looks like this. This is the signal. And then I have the two thresholds. These are the voltages when you add to V reference this delta due to the high or low output voltage. So this is the high threshold. This is the low threshold. So as the signal is going up, it'll hit the high threshold. And since it's going into the minus input terminal, then the output will go low because this will be higher than the threshold here. And once this will happen, then you move actually for this input to the lower threshold because now you have a different voltage drop here. And here it will be sustained until the signal goes below this low threshold. And as it goes below this threshold, then the output becomes positive. So here it is, and you actually jump now to a higher threshold between the signal and the reference. Now the memory effect comes in virtue of the fact that the amplifier or comparator is locked. That is, when the input here is high, this is high, so it's locked to one position. So this is one state. And then when the input here is low with respect to the minus, it goes into the low position. So it's another state. So you might say it's like a flip-flop going one way to another. And that's actually a memory which tells the unit which way or what was happening before the current state. Now let's go back now to this tutorial. This is a tutorial that is titled Designing a Schmitt Trigger Using Operation Amplifier for High-Speed Digital Signal. Well, first we see here, as I shown earlier, the effect of the two thresholds. This is the case of one threshold. If there is one threshold, this is the signal, move around it, then we're going to have an output. But if we have the two threshold, then of course it'll have a change when we hit the higher threshold, and then all the way it'll go until we hit the lower threshold, and then there'll be a change. So this is pretty much what I've shown before. Now the demo circuit is built around an operation amplifier LM741. Originally the name was MU-A741, and if I'm not mistaken, this is the first operation amplifier built by Integrated Circuit that appeared on the market. Okay, that's a very, very old operation amplifier. So what we see here again is the input. We see the feedback here, the positive feedback, and there is a divider here because the voltage here is high, so we like to put the reference to a lower value, and therefore there is an extra divider here. Now there is also a capacitor that I'll talk about it later on. So first of all, let me discuss the issue. What is the difference between operation amplifier or a comparator when it comes to a Schmitt trigger? So the symbols are the same, they look the same, so what is really the difference? And if you look at the internal circuitry of a comparator and an operation amplifier, you pretty much see similar circuitry. There is an input section, there is an output section, but there is one very important difference. And the difference being that in the case of the amplifier, you have this capacitor, and I'm talking about an internally compensated operation amplifier. Now, the purpose of this capacitor is to stabilize the system, because without the capacitor, there's too much phase shift, too much lagging, and it'll be almost impossible to close the loop from outside and stabilize the system. So all the vendors today are providing an internally compensated amplifier, which has this compensating capacitor. So what does it do? First of all, it stabilizes the circuit, but it actually is harmful. It's harmful for step responses. And let me explain it by this equivalent circuit, a simplified equivalent circuit of an operational amplifier. You have the input stage. This is the capacitor, which is usually implemented as a Miller capacitor so that you get effectively a higher capacitance. And this is the output section. So in this case, if you have a fast change or a step change, and this second stage or intermediate stage is actually fed by a current source, then of course, if you have a step change, then the rise of the voltage here will depend on the magnitude of the current and the capacitance here. And it will be like a RAM. And it will be limited to this rate. There's no way that this circuit can go at a higher rate. It is locked to the rate determined by this I and by this C. And then there is an amplifier, so actually it's amplifying, so in fact you get here a gain and therefore the rate here is faster. So very typically a operational amplifier, when you have a step input, that is, there is a need for a change, for a fast change, it will swing at a given rate, which is called the slew rate, and this is kind of limited because of this exact capacitor we are talking about. So if I look now at this tutorial, which is supposed to give us a solution for a high-speed digital signal, what I see here, this is the output of the 741. This is very, very typical. You see, this is now the rise time is about 50 microsecond. The change here is 10 volt. So it comes out to be about 0.5 volt to microsecond, very typical of internally compensated amplifier that you'll find now commercially. So if I look at the datasheet, this is exactly what they say. They say that the slew rate is between 0.3, 0.7, and we found that it is about 0.5. So this is very typical. Now, this means that the change here cannot be fast. So if you have fast pulses or high frequency pulses, the output cannot follow them because it takes it a long time to swing from the low level to the higher level. But there is another problem with the 741. Originally, this amplifier was designed for a bipolar operation. The way it is used here is a unipolar. This is a 12 volt and here is ground. Now, in this particular case then, the swing of the output is not from ground to the 12 volt. This is not a rail-to-rail amplifier. The rail-to-rail amplifier was invented many, many years after the 741 was introduced. So what we are going to have here is for a full swing, we have to have a sort of a difference of about 1 volt or maybe more, 2 volts to ground here, and to another 1 volt or 2 volt to the maximum. I don't worry about this. I worry about this because then if this is to be fed to a digital circuit, a 1 volt zero level is not something that you like to have. So this is not compatible with digital signals at all. Not to mention that the swing here is 11 volts, so maybe CMOS running at 12 volt, it's okay, but certainly not 5 volt digital logic or systems or microprocessor or whatsoever. So this is another issue with this tutorial. And if I look now at a modern comparator, which does not have this compensating capacitor, of course, because comparators are not designed or not intended to use in closed loop. They are intended to use in open loop. So therefore, you do not need this compensating capacitor. So in this particular case, this is just an example here of a comparator or a modern day comparator. You see that the rise and fall time, we are talking about 20 nanosecond. And this is for the full swing. output voltage swing between very close to 0 and then, no, this is sourcing, so this will be like the high level minus maximum 400 millivolt, and then to the low level, which is also maximum 400 millivolt. So this is pretty much like a rail-to-rail, or it is a rail-to-rail device, and of course the speed is quite a bit faster than we have been talking about in regard to the 741. If I compare now the output of the 741, which is intended for high-speed logic or digital system, and compare it to a comparator, this is the comparator I was just showing before, you see that here we're talking the scale here, okay? Look at the scale. This is 100 microsecond per division, and here it's 100 nanosecond per division, and here you see it even faster than this. So no question that the 741 or any other operational amplifier internally compensated is not for fast digital signal. It is okay if you have a very slow signal, you don't worry too much about the response time, then that's perfectly okay, but not if you want to respond to fast signal or high frequency pulses. There is another issue here, and that is, where would you like to feed the reference and where would you like to feed the signal? Well, the feedback is always to the positive, okay, it's positive feedback. But then you can have the reference here, signal here, or the signal here and the reference here. The difference is, first of all, regarding the output, is that in this case, as the signal goes above the threshold, you'll have a positive output, okay, a high level output. On the other hand, here, if the signal goes high, you get a low output. So this is one difference. Another difference is that in the case of feeding the signal here, you have to worry about the impedance of this source because it will be part of this divider which will determine the threshold. So you can do that, there's no problem in that, but be careful that R1 actually includes the contribution of the output impedance or resistance of whatever you have here to feed the signal. If it is an output of, say, of an operational amplifier, that's of course okay. But if not, you have to take it into account. Now, what about the threshold? Very easy to calculate the threshold because the threshold is really the voltage in between the signal and the reference when you have transitions. Now, the transitions are happening when the input to the amplifier itself or to the comparator itself, the inputs to the minus and to the plus terminal are equal. This is where this is the sensitivity of the amplifier. Now we are referring now to these two terminals, which are like the terminal of the Schmitt trigger, and the threshold we are talking about is referred to these. Now the difference is, of course, the voltage drop on this amplifier. So in one case, we're going to have the reference plus the voltage here due to the output high, or the reference plus the voltage here due to the output low. This could be, say, 5 volts, and this could be like close to 0. So the threshold can be calculated, say, for the high side by looking at, first of all, the difference here. This is the difference. And then you have a voltage divider here. So this is the difference times the voltage divider R1 plus R2. This is the delta V here that you add to V reference to get a high threshold. And the same thing here, the only difference is that now this is out low rather than out high. So this is the way to calculate the threshold. And of course, once you decide about these levels and you know what is the V reference, from these two equations, you can extract R1 and R2. So this would be the way to design the circuit. Now, what happens if I'm using, say, a divider like this in order to lower the voltage of the reference? I can use Thevenin in order to actually move from this configuration back to this configuration. Because if I look from here backward, I can describe this V reference and R1 and R2 as a equivalent V reference and some different resistance, the resistance being these two in parallel, and the reference, of course, is by this divider. So basically, you can go and first of all convert to this and then go back to this circuit. Now, in this tutorial, there are some equations for the threshold. Here is the threshold for the high and low threshold, and here are the expressions. Unfortunately, we can't identify what is R sub B and R sub H because they are not marked on the circuit. So just to check to see if it makes sense, this equation, I've sort of set all these resistors to be equal. Well, I said 1, could be 1 kilo, doesn't matter. So putting all these 1, I have here 1, and then this will be 1 and divided by 2. Okay, this is 1 divided by 2, and I get the threshold 24 volt. Just doesn't make sense because this is 12 volt. So this equation is certainly unacceptable and there's an error in it. And since, as you can see, these expressions are pretty much the same when R is 1, although the resistor are the same, so I'm getting 24 volt here. So obviously these are incorrect. So this is one more problem with this tutorial. Now in the tutorial or in the demo circuit, there is a capacitor here and nothing is said about it. So let me explain what could be the purpose of such a capacitor that sometimes you'd like to put in. So first, let me point out to some problems that we might have. One problem is a small overdrive. If this is the reference, the threshold, and the signal is going up and then sort of stabilizes just above the threshold, this difference is called overdrive. This is how much I'm higher than the threshold or the reference in the case of a comparator, okay? This is the characteristic of a comparator. And as it turns out, the larger the overdrive, the faster is the response. So if you have a very small overdrive, say a couple of millivolts above the reference voltage between the two terminals of the comparator, then you're going to have a very slow rise. This is very typical of comparator. So this is one problem. Another problem is that when you are just approaching the transition, that is when V plus is equal to V minus and the V out is starting to move, you are in fact in the linear region. You are in the linear region and there is a positive feedback. You might have oscillation here. So this will be found in some cases that depending on the parasitic capacitances, the type of amplifier, you might have a oscillation due to the fact that you have a positive feedback and you are in the linear region. So one way to combat this would be to put a capacitor. Now what happened with the capacitor is that it sort of accelerated, speeding up the change and very quickly moving to the other state and locking the amplifier to the other state. This would be one purpose of this capacitor, and once it is changing, then it is actually changing the voltage here, so it's actually increasing the difference between the signal and, say, the reference. Unfortunately, it takes some time for this to recover. So you have to take into account that if you put a capacitor, there is a certain dead time here that you will not be able to recognize another pulse that will be coming in. So the capacitance here shouldn't be too large because otherwise you are blocking some of the time, and if you have another pulse coming in, the circuit is actually locked and it'll take a while for the RC to discharge. So regarding the tutorial entitled Designing Schmitt Trigger Using Operational Amplifier for High-Speed Digital Signal, what I found is that there are many issues with it. First of all, it's not high speed. Secondly, the power supply is 12 volt, which is really not suitable for digital system. And then we have a voltage level issue. The zero level is just too high. And then we have wrong equation for the threshold. And there is no explanation of this capacitor. So this tutorial really leaves a lot to be desired. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you have found it of interest and perhaps it will be useful to you in the future. Thank you very much.